June 1990. The Soviets were about to do it again. Not since Sputnik had they so dramatically outpaced the West. They were about to deploy the most advanced vertical takeoff and landing combat aircraft the world had ever seen. The Yak-141, NATO reporting name Freestyle, didn't just outperform the legendary British Harrier, it made it look ancient. Everything the Harrier could do, the Yak-141 could do better. While the Harrier struggled to break the sound barrier, Freestyle blasted through the sky at Mach 1.7. Its revolutionary rotating rear nozzle allowed for 95-degree thrust vectoring transitions in seconds, delivering helicopter-like hovering with fighter jet performance. The digital fly-by-wire system allowed a level of control Western pilots could only dream of. Then the unthinkable happened. Yak-141's DNA would soon take flight in American colors. A wild idea. World War II had made something clear. Aircraft were as powerful as they were dependent on airfields and runways. Runways were painfully vulnerable and unreliable. In addition to the emergence of early rotorcraft and helicopter designs, this led engineers to reimagine combat aircraft. What if a warplane could take off vertically like a helicopter from even the narrowest patch of land, and yet transition into the speeds and maneuverability of conventional fighter planes? Surely that would be revolutionary. Soviet visionaries didn't want to be left behind. Early experimentation, such as Boris Yuryev's ambitious 1946 Kit-1 project using the VK-1 OB-powered engine, hinted at the possibilities of a powerful VTOL aircraft emerging in the near future, but ultimately fell short. The turning point came with the arrival of turbojet technology. Captured German turbojets like the BMW 003 and Juncker's Umo 004 initially powered aircraft like the Arado AR-234 and the Messerschmitt Me-262. Soviet designers saw an opportunity. They might achieve VTOL performance by supplementing aerodynamic wing lift with vertical thrust. In 1947, Alexei Shcherbakov envisioned a high-speed fighter with swiveling wingtip power plants. Testing on static rigs using twin Umo 004 engines provided a glimpse of the promise of jet lift, even if practical flight remained elusive. However, Soviet interest in jet-powered vertical thrust dimmed until the early 1950s. Meanwhile, in the West, research was gaining momentum. The British Rolls-Royce thrust-measuring rig, affectionately dubbed the Flying Bedstead, made its initial hovering flights in 1953, capturing global attention. This success forced a Soviet response. A group of dedicated engineers at the Ramenskoye Flight Test Institute, under the guidance of A.N. Rafaelians, pushed forward. By 1958, they had built the Turbolet, a test bed that mounted a single vertically oriented Mikulin RD-9BL turbojet. Equipped with innovative puffer pipes for jet reaction controls and modest thrust vectoring via swiveling vanes, the Turbolet managed to hover. However, its flight endurance was limited to around 30 minutes. Its compact design and experimental control system were a far cry from the more developed Western VTOL test platforms. Still, they were a step in the right direction. A lesson from the British. In the early 1960s, the inspiration for a revolution in Soviet VTOL design came from an unexpected source: an airshow visit. A delegation, led by the renowned aircraft designer Alexander Yakovlev, visited the 1960 Farnborough Airshow, where the British short SC-1 performed daring VTOL demonstrations. The SC-1, powered by 4 vertically mounted Rolls-Royce RB-108 lift engines, supplemented by a horizontal jet for forward propulsion, demonstrated that VTOL was feasible, effective, and reliable. Yakovlev was so impressed by these performances that he immediately recommended that Soviet research take a similar leap forward. While Soviet research had produced promising prototypes like the Turbolet, these machines lagged behind the West in terms of operational efficiency, stability, and performance. Spurred on, Yakovlev returned to Moscow with a vision. He began reimagining VTOL technology by drawing on his earlier work with the Yak-30 light jet trainer. His team initially considered a concept named the Yak-30V that would retrofit the trainer with 2 vertically mounted engines. Yet the rapid evolution of VTOL technology rendered this approach obsolete before it could even be developed. Instead, Yakovlev's engineers set their sights on a more ambitious design, a machine that could harness the power of thrust vectoring via rotating nozzles, a technique that promised far greater control during the critical transitions between hover and forward flight. Their efforts materialized in the form of the ambitious Yak-36. This groundbreaking prototype integrated advanced automatic flight control systems developed from turbojet experience. The Yak-36 was proof that not only the West could come up with technological breakthroughs, combining dual vectored thrust engines with a compact, agile airframe to create something unprecedented and truly remarkable. Yet, as the Yak-36 took its historic first untethered hover in January 1963, and later completed its full transition to horizontal flight, its limitations became all too apparent. Compared to its Western counterparts, which rapidly evolved with more powerful and efficient engines and more sophisticated control systems, the Yak-36 struggled with marginal thrust-to-weight ratios and a delicate balance of jet lift and aerodynamic forces. The challenges of exhaust gas recirculation, adverse ground effects, and insufficient engine power hampered its performance and demonstrated that the Soviets were not as far as they believed they were in VTOL technology. The inadequate engine thrust, limited flight endurance, and unstable control during transitions revealed a fundamental truth to Soviet designers. While the early VTOL prototypes demonstrated the feasibility of vertical flight, they were ultimately constrained by the limits of existing technology. The Western projects, notably the British efforts that later matured into the Harrier, offered operational capabilities that the Soviet machines could not match. The single nozzle breakthrough. Yakovlev, fueled by years of experience as well as frustration, gathered his team to define the blueprint of a supersonic successor to the Yak-36 and Yak-38 Forger series. The project, initially known as Yak-41, was destined to become the breakthrough the Soviet Navy was so desperately waiting for. The Navy's requirements were exacting. The new interceptor would incorporate a powerful S-41 radar and deploy the potent R-27 medium-range air-to-air missiles, technology closely related to that which powered the agile MiG-29 Fulcrum. Yakovlev was joined by the capable hands of Alexander Levinskik, Viktor Pavlov, and later Konstantin Popovich, a band of dedicated engineers and technical innovators united by a common goal: to conquer the complex challenges of vertical takeoff, supersonic performance, and shipborne operations. They understood that to leap forward from the Yak-38's limitations, they needed to develop an advanced airframe and a revolutionary propulsion system. Drawing on the hard-earned lessons of the Yak-38's development, the team devised a composite power plant system centered around a single nozzle. It was a massive gamble that could streamline the entire design and functionality of the aircraft or end in disaster. But it paid off, simplifying the integration of afterburning while adhering to strict fuselage cross-sectional area requirements. This single nozzle, they reasoned, would weigh less than the complex vectored thrust turbofan found in Western designs such as the Harrier, and it was key to achieving the much-coveted supersonic performance. But it was easier said than done. The engineers explored several alternative layouts in painstaking detail. One early concept was a variation of the Yak-38 without the use of dedicated lift engines. This design soon proved to be a dead end due to the complications it introduced in hover control. Another daring proposal involved an aft-mounted lift and cruise turbofan equipped with a flat thrust-vectoring nozzle, where discrete outlets for cold and hot gas flows were meticulously planned. In this design, cold flow gases were to be ducted to a small afterburner chamber located in the forward fuselage, acting as a balancing force. Yet this solution was abandoned when detailed calculations revealed that the necessary ducting would force an unacceptable increase in fuselage diameter. One last shot. Months turned to years, and with no major breakthrough, the project seemed doomed. However, the team revisited the design in 1979, drawing inspiration from the Yak-45. This earlier twin jet fighter project had lost out to the likes of the MiG-29 and Sukhoi Su-27 flanker. In the original Yak-45, twin Izdelia-69 turbojets were mounted in underwing nacelles and coupled with rectangular vectoring nozzles in the VSTOL variant. Although the Yak-45's radical, tailless canard configuration, complete with a shoulder-mounted cranked wing and centrally mounted RD-38 lift engines, ultimately proved too ambitious, it provided invaluable insights into the design challenges of high-performance VTOL aircraft. By 1980, Alexander Yakovlev returned to the drawing board with renewed vigor. The focus shifted to a new high-power afterburning lift and cruise engine, the Izdelia-79, later known as the R-79. Developed by Moscow's Soyuz Design Bureau Under the guidance of Oleg Favorsky and later Vasily Kopchenko, the R-79 was a technological marvel. As a mixed-flow turbofan, boasting a bypass ratio between 0.9 and 1.2 in forward flight, it featured a 3-stage low-pressure compressor, an 11-stage high-pressure compressor, and 2 contra-rotating turbines. Complementing these mechanical wonders was a triple-redundant analog electronic fuel control system backed by hydromechanical failsafes, ensuring that the engine could meet the brutal demands of supersonic flight and the rapid thrust modulation required for vertical takeoffs. The R-79's design thrust was a mind-blowing 152 kilonewtons in conventional flight mode, with a maximum dry thrust of 107.9 kilonewtons, all while maintaining a dry weight of just 2,750 kilograms. With a length of 5.229 meters and a maximum diameter of 1.716 meters, this warplane was meticulously engineered to conform to the strict spatial constraints imposed by carrier operations. The flat thrust vectoring nozzle, though ultimately abandoned in favor of a circular tailpipe afterburner design, remained the constant source of debate and ingenuity among the engineers. Parallel to the development of the primary propulsion system was the equally critical challenge of designing the lift engines. This is where the RD-41 came in, a lightweight single-shaft engine aimed at delivering an additional 40.21 kilonewtons of thrust. This engine had to meet exacting requirements. Its diameter was strictly limited to 0.635 meters by the aircraft's area-ruled fuselage dimensions, and its exhaust temperatures were capped by the thermal tolerances of the carrier deck. In designing the RD-41, the engineers increased the compressor stages from 6 to 7 and integrated digital electronic fuel and power controls. With the extensive use of titanium and a 6.25 compression ratio, the engine achieved a thrust-to-weight ratio comparable to that of the celebrated Rolls-Royce RB162 lift engine. One of the most challenging aspects of the project was the integration of these disparate propulsion systems into a cohesive whole. Unlike the YAK-38, where the lift engine and the primary power plant's nozzle thrusts were arranged symmetrically around the aircraft's center of gravity, the supersonic YAK-41 faced additional complications. The vectoring afterburner of the R-79 produced a colossal 122.6 kilonewtons of thrust in vertical mode, while the combined output of the two RD-41 engines amounted to only 80.42 kilonewtons. To make sure that the aircraft maintained balance during critical vertical takeoffs, engineers had to position the R-79 nozzle closer to the aircraft's center of gravity, thereby slashing its moment arm. This resulted in the YAK-41's twin-boom airframe design. The configuration would become a defining characteristic of the aircraft. The twin-boom layout, similar to the Mikoyan MiG-31 Foxhound, featured a shoulder-mounted 30-degree swept wing paired with twin tails. The deep, slab-sided booms housed the fins and stabilizers and served as structural reinforcements, their inner surfaces lined with titanium shrouds to protect against the intense heat emanating from the R-79 afterburner. Running out of time. The development process was arduous and filled with gut-wrenching setbacks. During one phase, the design team proposed relocating the lift engines forward of the cockpit, an innovative idea intended to widen the separation between the vectoring nozzle and the lift engines to increase the moment arm and improve stability. However, the need to accommodate a radar intake in the forward fuselage, combined with the risk of ingesting hot exhaust gases, forced the team to abandon this radical layout. Flight testing of the prototypes began in earnest in the late 1980s. The first prototype, known as 75, took to the skies on March 9, 1987, at the Zhukovsky Flight Research Institute near Moscow. Yakovlev's chief test pilot, Andrei Sinitsyn, piloted the aircraft in a conventional wing-borne takeoff and landing configuration, with the R-79 nozzle locked in its horizontal position. As flight testing progressed, the YAK-41 prototypes, 75 and its sibling, 77, began to reveal both the design's promise and pitfalls. The aircraft demonstrated its ability to transition seamlessly between conventional flight and hover, thanks in large part to a sophisticated digital fly-by-wire system and integrated engine control. These afforded the model a sophistication previously unseen in Soviet aircraft design. It allowed for electronic modulation of both the main engine and lift engines, using subtle RPM variations to fine-tune thrust and maintain stability during low-speed operations. Yet challenges remained. One of the most irritating problems was achieving continuity of afterburner operation during vectoring. a process that involved mechanically rotating the 3 circular tailpipe segments to direct thrust over a range of 95 degrees. The engineers struggled to maintain efficient combustion in these complex gas flows while preventing excessive heat from damaging critical structural components. A unique cooling system was designed, and the problem was eventually solved through a novel, closely guarded method that remains classified to this day. The aircraft's aerodynamic design was equally ambitious. To maximize payload and extend range, the YAK-41 was engineered to perform rolling takeoffs and run-on landings, a departure from the pure VTOL operations of its predecessors. During these operations, the 2 RD-41 lift engines were inclined aft by about 15 degrees to contribute additional forward thrust, while their swiveling exhaust nozzles could be directed up to 9 degrees forward or 17 degrees aft. These adjustments allowed the YAK-41 to accelerate to speeds of approximately 537 kilometers per hour within 18 seconds during a rolling takeoff, a performance that belied its unconventional appearance. But time was running out outside the hermetic bubble of the Yakovlev team. Funding constraints and the inexorable tide of political change passed from distant possibilities to pressing issues. In the design bureau's cramped laboratories and wind tunnels, heated debates and late-night calculations became the norm. Every modification to the RD-41 or the R-79, every reconfiguration of the airframe booms and tail surfaces was a step toward perfection, a perfection that was as much about engineering as it was about national pride. The collapse. By 1991, the YAK-41 had set new performance records and earned its provisional NATO reporting name, Freestyle. Test pilot Andrei Sinitsyn, whose record-breaking flights had already rewritten the performance envelope of VSTOL aircraft, became a symbol of the project's potential. In a series of daring maneuvers, Sinitsyn set 11 new Class H world records, including a maximum VSTOL altitude of 13,100 meters, with various payloads and unprecedented climb times. It was clear now that the YAK-41 was not only a technical marvel, but also a remarkable combat aircraft in its own right. Then it came. The collapse of the Soviet Union was a punch in the gut of the Yakovlev Design Bureau, and the once generous state funding was rapidly drying up. In a dramatic turn of events, a catastrophic landing accident in October 1991, caused by an excessive vertical descent rate, resulted in severe damage to one of the prototypes and nearly claimed the life of a test pilot. Although the emergency ejection system functioned and he escaped with only minor injuries, the incident accelerated the collapse of the project at a time of increasing uncertainty. But Yakovlev was not letting his revolutionary brainchild be taken away from him so easily. Desperate to lure additional backing, surviving prototypes were showcased at major international air shows, most notably at the 1991 Paris Air Show and later at Farnborough in 1992. These public demonstrations were as much a bid for international partnerships as they were a celebration of the aircraft's technological achievements. In a series of conventional takeoffs and landings, augmented by precise rolling VTOL maneuvers, the YAK-41 was now marketed as the YAK-141 for export. Internally, the Yakovlev team continued to refine every aspect of the aircraft. Advanced composite materials made up nearly 26% of the airframe, providing strength and durability and reducing the overall weight, a critical factor for achieving the desired thrust-to-weight ratios. The cockpit was fitted with a state-of-the-art K-36LV rocket-boosted 0-0 ejection seat, modified from the YAK-38's SKEM system to accommodate a broader range of pitch and roll attitudes. The integrated weapon system, derived from MiG-29 technology, was designed to allow the aircraft to switch seamlessly between air defense and ground attack roles, with provisions for a suite of armaments ranging from 30mm cannons to a variety of air-to-air and air-to-surface missiles. As promising as the YAK-141 was on the test track, its tactical characteristics were quickly being overshadowed by the emergence of competing designs, even domestic ones, like that of the Sukhoi Su-27K flanker. With superior range and payload capabilities, the Su-27K threatened to eclipse the YAK-141's role on the Soviet Navy's carrier decks. Moreover, the political upheaval the Soviet Union was going through, and the resulting reallocation of defense budgets, meant that state support for such cutting-edge projects was becoming a luxury of the past. Even so, the Yakovlev Design Bureau, driven by the spirit of innovation and the personal resolve of its team members, sought to carry the legacy forward. Plans for an upgraded version of the aircraft, one that would push payload and range limits even further, were drawn up. This version, still designated under the Yak-141 moniker, promised improved engine thrust, increased internal fuel capacity, and refinements to reduce radar and infrared signatures. An unprecedented deal. In a matter of months, the Yak-141 went from being on the verge of becoming the Sputnik of Soviet combat aviation to being a struggling project in dire need of funding as the new Russian Republic readjusted its defense budget. America, which had long scrutinized the Yak-141 project, leaped to gain an advantage. In its blend of vectored thrust, integrated flight control, and agile handling, they saw the seeds of a new design philosophy that transcended traditional fighter roles. In classified research briefings and international airshow demonstrations, U.S. military analysts studied the Yak-141's daring integration of technologies and approached their developers. While its limitations were something the Americans knew very well, the aircraft's ability to transition seamlessly between vertical takeoff and high-speed supersonic flight was invaluable to American engineers. They were captivated by the performance under extreme conditions, especially its rapid attitude adjustments during critical flight phases, which challenged prevailing assumptions about VTOL performance envelopes. These insights spurred American research labs to explore hybrid propulsion systems that could reconcile the conflicting demands of vertical lift and forward aerodynamic efficiency. The final situation grew unsustainable for the Yakovlev Design Bureau, so much so that they were facing the cancellation of the Yak-141 project and the closing down of the entire corporation. Facing the end and seeing that the Soviet Union no longer existed, and they were free to negotiate with foreign nations, they decided to do the unthinkable. On September 6, 1992, Yakovlev announced signing a $400 million agreement between his firm and Lockheed Martin, giving the American arms manufacturer access to the Yak-141's blueprints and VTOL data. Around this same time, the U.S. was working on the Joint Strike Fighter, or JSF program, which required a next-generation VTOL aircraft for the Marine Corps. Using the Yak-141's vectoring nozzle design, wind tunnel testing data, flight performance reports from Yakovlev, and the help of Russian engineers who had worked on the Yak-141, Lockheed Martin was able to not only implement the technology, but quickly improve it to unprecedented levels and draft the design of what would become the American F-35B combat jet. They integrated state-of-the-art composite materials and sensor fusion technologies to create a platform that could fly vertically, provide air superiority, and demonstrate stealth capabilities for an entire new age of aerial combat. Lockheed Martin used the Yak-141 data not to create a replica, but as a starting point to advance their own VTOL solution without having to start from scratch. The legacy of the Soviet prototype, despite the collapse of the USSR, became the cornerstone of a broader technological evolution. It helped transition VTOL aircraft from experimental curiosities of the Cold War into the backbone of modern air power, albeit in the hands of the Soviet Union's greatest rival.